doing time-sensitive experiments with FPGAs. So, is it gonna want to change the slide? There we go. So, as Nathan was saying, what is an FPGA? Well, it stands for Field Programmable Gate Array. Basically, these are chips that contain thousands of logic array blocks, also called labs. Stands for labs. They're also called configurable logic blocks, depending on which manufacturer you're buying from, because they like to use confusing different language. Each of these blocks contains registers and configurable Boolean logic, and they are very useful when frequent redesigns to circuitry needs to happen, because otherwise you're using ASICs, which are very inconvenient. So an ASIC is an application-specific integrated circuit. Basically, it's any computational processor designed for a specific purpose. An example would be a graphics card, if for gaming, or example, machine learning cards. Sometimes they're adding cards for that. The CPU is almost pretty much an ASIC too. So in this case, you could make any of those on an FPGA. You can make an FPGA handle graphics output. You could make it via CPU. In fact, many people do have that on there. All right, so a closer look at these logic array blocks. They work using something called lookup tables. Essentially, these lookup tables are, they get programmed with a certain mask. It's just a series of ones and zeros that tells them what Boolean function to replicate. So any true false function. So any n input, n output Boolean function you can make as long as you have enough logic array blocks left, because there are a finite amount of them. There's also a lot of dedicated logic for various common tasks. For example, right there marked FA is a full adder. So if you're doing a lot of arithmetic, these full adders would be more efficient than like trying to build your own full adders out of lookup tables. So if you're just adding two binary numbers together, that full adder would come in and do that instead of you having to make your own adder. There also is dedicated circuitry for doing floating point multiplications if you're working with decimal numbers. I actually saw a class project, because Cornell teaches a class on these, and a class project they did was they actually made a hardware accelerated Mandelbrot fractal zoom. So some of you may have seen a Mandelbrot fractal zoom zooming in on an infinitely complex thing, all kinds of pretty colors and stuff. But by building the circuitry purpose-built, they were able to do it much faster in the CPU, even though this thing has a much lower clock speed compared to a modern CPU, less advanced in a way. So you can get a lot by having dedicated circuitry for a task. So an example of some circuitry we'd like to put on these boards would be a time to digital converter, hence the timing in the title. These essentially let you assign a time to when a signal arrived. They are useful in a variety of applications. For example, LiDAR. Self-driving cars wouldn't work too well if they can't find their way around. They shoot out some light and they measure how long it takes to come back. But that happens very fast because light is fast. So you need to have very high resolution. So commercial versions of these can cost as much as $28,000. That is how much our research group, Dr. Gauthier and Dr. Lafayette, my PIs, paid for a system that does this just recently. They can be very expensive. But this board that we're using costs just $100. So that's quite a bit improvement. If we can get anywhere near the performance of that device with a $100 board, then it's worth it easily. So these get a resolution on the order of 10 picoseconds. So that's about 10 to the minus 14 seconds. And that's using various little clever bits of circuitry. But a naive way to make a time digital converter is what you see in the image down there, a tapped delay line time digital converter. So essentially, a signal travels down the denoted signal line here. And as it goes through each of these buffers, there's a certain delay that's well known. Let's call it tau. So tau, we can cut about 220 picoseconds in the case of what we're doing on our boards. So we know that each time it passes over a tau, that is now 220 picoseconds that's advanced. So a clock comes in, And the clock triggers these circuits here. These are flip-flops. Essentially what they do is they just freeze the state of this wire in time so you can look at it later. It's how computer memory works. So it comes in at what's called latches, and then you can just read out exactly where the signal was as it was traveling through this delay line. So you can get a snapshot of where it was as it was traveling through. Because it takes a well-known amount of time to travel through there, you can look at it and say, okay, hey, it made it halfway through, so we know it took half of the amount of delays that we have to get there, so we know when it arrived. And that can give you some and just even that naive approach can give you like 200 some picosecond resolution. So the big thing is now we got to say, okay, what's that tau? I told you what it was kind of, but we now know the accuracy of that. Like what's the standard deviation? How are we going to quote our error if we did a measurement with this? Because we can't just call an exact number. They'd look at that, okay, why they have an infinite precision device or something. So we use things called ring oscillators to do that. Ring oscillators are just a logic circuit containing an odd number of inverter gates. So they just take the logic that's put into them and reverse it. So true becomes false, false becomes true. And essentially that switching of the logic, because there's an odd number, they don't match up. So they oscillate, switching that signal. So if you were to put a little scope right here on like one of these wires, you would see a wave such as this in voltage. Just a simple little square wave. And by measuring the frequency of that square wave, denoted F here with N ring oscillators, you can get the tau. So the idea is we build these ring oscillators, measure their frequency, and then we have characterized the delay. So here's an example of what a ring oscillator looks like. I made this in Minecraft because why not? You can build logic circuits in Minecraft, and I think this makes a pretty good visualization. So the state of each inverter essentially is represented by that redstone lamp that's on or off, and you can clearly see it just propagating around there in that square wave. So I found this to be a pretty great visualization for how a ring oscillator works. So the general measurement methodology here is that we define each ring oscillator as sort of a black box module. It has an input and an output, well, an output pretty much. And then we just stick it all around the board. And then we have some central circuitry that just counts it. It counts each time it hits a rising edge of that square wave it makes. So it counts basically how many cycles it makes per our control clock. Yeah, so we essentially read out that value of the ring oscillator while we increment a counter up from that ring oscillator for a certain known number of clocks. Our control clock is about 200 megahertz. So we say wait a certain number of clocks, we know how many seconds that was, and then we can say, okay, that was then the frequency of our ring oscillator. So in order to do all this though, we need to then get that information off of the chip. And we do that over what's called a Jtag interface, which I can't remember what it stands for. I'm not sure if I ever knew. But basically, using the software that's used for development on these boards, we can place RAM, like computer memory, on these boards, write that data that we get for each ring oscillator into RAM, and then read it off using some Python that we wrote. And actually, some people from my research group have written Python packages to work with these. You can download them as you would NumPy or other Python packages. They're called Quartus FPGA, Quartus TCL, and MIF. I contributed, I think, a little bit of code to Quartus FPGA. That's the most recent one we put out. But of course, we had problems, as you will with any attempt to measure anything. One thing we saw was strange behavior when starting the ring oscillators. If we started measuring them right away, they just gave us all kinds of nonsense values. So we had to wait a little bit to sort of let them stabilize. We also had a problem of crossing clock domains, and that's a bit of a tricky problem, comes up in electrical computer engineering a lot. But basically, if all your logic is being executed on a clock in one area of the board, and then you have another clock in the other area of the board, it's actually kind of difficult to pass data between them because the logic can only evaluate itself when the clock hits. So essentially we just worked our way around that problem by directly reading the counter, so directly making a counter circuit that increments a value in memory as the ring oscillator goes around. And then we just read that value off by the clock and hope it doesn't collide, essentially. We experiment some things. You could sort of like disable the ring oscillators. I believe actually in the latest version, we stop the ring oscillator, then read that to prevent that sort of collision. Because if it's trying to write to memory when we're reading from it, then we get garbage. Another issue we had, which has been a very persistent one, is multiple pulses going around the ring oscillator. And you can see an example of this right here in this histogram. There's a little tiny data point right out there. That's why this x-axis is so spread out right there that just out of spite does not want to cooperate. So yeah. Okay, so the register latching issue. So yeah, as I said, the solution mainly was to put a little check in there. We had a signal we could send to it, and it wouldn't increment that counter unless we told it it could. So then we get rid of that signal, and then we can read out the counter with no worries about the collision. But for the multiple pulses in the oscillator, though, basically, for ring oscillators of a certain size and larger, they can create higher harmonics, basically in them. There can be multiple changes in logic propagating around the ring at the same time. What we most typically saw was a 3 times increase, indicating the presence of 2 additional pulses. And basically, it can only support odd numbers of pulses. So when we were looking at our counting circuitry, we just started to see some that were 3 times as fast as we thought they should be. Rather consistently 3 times as fast. So here's an example, another Minecraft visualization of what those multiple pulses going around a ring oscillator looks like. This one's a bit harder to make sense of, but you can sort of see it's in the places where the 2 lamps are lit up right next to each other is where a pulse exists at any given point. So you can kind of follow one here and move kind of fast. But basically, there are 3 pulses going around, and it's going to create a waveform such as this, which, since we're counting the positive edges, the rising edges of that signal, 1, 2, 3, 1, 2, 3, getting 3 times that each time. So the solution that we had was to replace one of the inverters with a NAND gate, so a not AND gate. This will basically behave like an inverter gate as long as an enable signal there is put into the gate. So this lets us control essentially whether the inverter has an odd or even number of inverters in it. So we can kind of make it act like it has an even number that will kill all the pulses around it and put it into a stationary known state. And then we can flip that signal and it will behave normally and we won't get outliers, which that pretty much solved our problems. However, we saw a large increase in the variability of the data. That NAND gate required more logic than our simple inverter gates would. So we could not, it was useless to us. We were losing too much information because of the variability introduced by that NAND gate. So we just decided to throw out the data, which you shouldn't do. But because it was very consistently 3 times and we thought we pretty well understood why this was happening, we felt a bit more comfortable throwing it out. And here's a nice histogram with the data being thrown out. And there's, as you can probably notice, there's a bimodal distribution there, which we still don't have a very solid explanation for. But I can give sort of a basic one, is that there are kind of 2 different types of labs on the board. And we noticed that there's labs and things called M labs. And we noticed that most of the M labs are over here in the second peak, but not all of them, of course. And also there are some labs over in the second peak. So we said, okay, well, time to look for some location-specific correlations. See if we can find any sort of correlation between the delay and the location around the board. See if that can give us any clues. So here's a color map sort of looking at that. And as you can see, there's some pretty clear vertical line correlations with this. Like the variability tends to be pretty localized to just a single column. And we actually found that the width of our distribution was much smaller if we just looked in a column. So that means if we were going to make our time-sensitive circuitry, our delay line of our TDC, we would want to put it in a column because we could better understand what's happening. We could essentially have a better guess at what our delay is. And it's more reliable measurements. And then we also wanted to look at the variation across the different boards. So I worked on this with Peter Menard and Caitlin Patterson over this past summer. And so these are measurements from our 3 boards. As you can see, that's not wonderful. Like they do vary by a pretty significant amount, almost 10% between board 3 and board 1, for example. Like that's not great. So that means if we were going to be doing any sort of time-sensitive work, we could say, okay, we make some sort of GitHub project that people could just grab and turn their boards into a timing circuit. We need to make some pretty careful calibration. And other people in our group are actually working on a sort of calibration algorithm where the board can just sit there and calibrate itself, which is pretty cool. So overall, there are some, we aren't the first people to try to look at this, of course. There's a previous paper that looked at this on an older version of these boards, I think almost more than 10 years ago. And we still don't have as good as their results for the variation. They did a bit of extra attempts to get sort of a quadratic fit to what was happening and everything, but overall, we're still seeing more variation than them, which could either tell to the manufacturing process of these modern boards or to our measurement methods. Still a bit inconclusive about that, but we are, at this stage, we're thinking we have a good idea of what's happening on there. And we have a decent idea of what we need to look out for when making a TDC, a time digital converter. A graduate student in our group, he is working on making a time digital converter just straight up. And he's doing, he's actually using those full adders that were in the logic array blocks that I showed earlier, not the lookup tables. Because he can get much less shorter delays with those on the order of, I think, about 8 picoseconds. Compared to the 220 we're seeing with these inverter gates, that's massive. And he can get extremely precise controlling. And he was using essentially that tap delay line circuit that we showed, but just using the carries instead of that. And he was able to get much more precise control. Like we could see graphs of just these pulses that are only a couple picoseconds in width, and we could just see them. It's pretty cool. And we also want to investigate variation among different boards. So we just had the 3 among us, but there's another research group that our research group collaborates with that has about 30 of these boards. And at some point, we're going to reach out to them and have them run our our characterization code that we've written all in Python scripts to just automatically grab this data on the boards, so we can get a better idea of how these vary across manufacturing lines. As well as also looking at how this variation goes over time. And actually, this was just today that my professor proposed this, is he thinks that after the first couple 100 hours of operation, we can actually see a significant difference in these delays. So it might be worthwhile for research groups wanting to do this to do sort of burn-in like you might with speakers or headphones and just run them nonstop to sort of get rid of that variability. Because most of it happens early on in lifetime, but also a good bit happens over time too. So characterizing that would also be important, because it may be that you need to recalibrate your board frequently. Otherwise, you're going to no longer have the results you think you have. So, yeah. I think that's about all I have.
Well, thank you. Does anyone have any questions? You've certainly given us quite a lot of time to ask. I did actually. Yeah,
this was adapted from a shorter presentation.
Well, we asked you to present on short notice, so it's pretty much our fault. At any rate, I did want to ask real quick. You're still working for Dr. Lafayette and Dr. Gauthier, right?
Yeah.
So are the timing circuits you guys are looking into for specific other applications in the research groups? I know you talked about at the beginning that this stuff is important in LiDAR, but what's the specific reason you guys are interested in it?
Yeah. So let's see. Okay. So there's actually a number of experiments in our field, quantum information science, that we need these precise timings for. So for example, an example experiment that Dr. Gauthier gave me to talk about in the presentation I just gave yesterday to the American Physical Society thing was a fluorescence lifetime decay experiment. Basically, you take a pulse laser and you shine it on a sample, and then you observe the fluorescence that comes off of it and time correlate that with the light that you sent. And they can tell you a lot about the optical properties of a material. Another example would be characterizing single photon sources. So a graduate student in our group, her name's Anita, she's working on characterizing hexagonal boron nitride, which is a sort of two-dimensional material like graphene. It's actually laid out in a hexagon just like graphene, but with boron and nitrogen atoms. And essentially imperfections in that sort of crystal lattice can produce very reliably very small amounts of photons. So characterizing that behavior to use them as then single photon sources in such as like interferometry experiments, such, that's very important. Yeah. It also comes in a lot with other area of work that our group does, which is SNSPDs, or superconducting nanowire single photon detectors. These are just very high efficiency light detectors that can detect single particles of light that you then combine with a time tagger, and then you can get these very accurate measurements. Caitlin, you raising your hand?
So TDC by Friday then?
Yeah, TDC by Friday. Dr. Lafayette has had a bit of an aggressive timeline. Halfway through the summer, he was saying TDC by Friday. We don't have a TDC yet. But yeah, any other questions? Happy to take them. Or just questions about, I don't know, anything, experimental physics in general, stuff at our group. Whether quantum computer AIs are going to take over the world, I don't know. Sam, are you on?
Yeah. So you'd said you're characterizing single photon, or they're useful for characterizing single photon emissions. So, or for timing it, I assume. So is that kind of what this work you're looking to like? Is that kind of the big picture of this work, is to eventually apply it to their, like, within your group?
Yeah, that was the hope. We of course have this $28,000 time tagger, which is quite nice and has nice software that works with it. But yeah, the idea is also that we can then tell people about this, and that optics labs, maybe less of a budget, could do experiments and have decent equipment for it at a very low cost. Yeah, especially in, let's say, in other countries, research budgets tend to be a lot smaller than they are in the US. So having solutions like this is quite nice.
Very cool, thanks.
Since this is the first time I've ever seen you as a person, I guess why optics, and why do you, and you may have answered this 100 times, and I'm sorry, but I'm just curious, why optics, and how did you get to do this stuff with to the point that you are doing it as of today?
So how did I find interest in this? at first, or like?
Yeah, and then how did you pursue it?
Okay, well, so in terms of finding interest in it, I had that typical college identity crisis somewhere around sophomore year, like, oh crap, do I even want to do physics? And then I read about a bunch of research groups, and this research group's work just interests me the most, partially because buzzword quantum computing was in there all over the place. And they also did some work with quantum key distribution, which is really cool because I'm interested in cryptography as well. So they're even doing it between 2 drones in flight and everything. But basically, yeah, so I got that initial interest. I emailed Dr. Gauthier. He didn't respond for 3 months. So then I went and badgered him for a while until eventually he pointed me to Dr. Lafayette, who had a project that they needed undergrads for. So I kind of strong-armed my way into the group just out of pure annoyance. But once I was in, I just really found I just liked working on these technical problems. Is oh, hey, we want to do this experiment, because most of experimental physics is you come up with the experiment you want to do, and then you spend 6 months trying to get the experiment to work. So it can feel a lot like engineering at times. You're not like doing glamorous physics all day. You're tinkering. You're trying to figure out why the hell this isn't working. Oh, your solder joint's bad and it came loose in the cryo chamber. That's fun. So now you got to resolder that. All the things like that. And I just found that I just enjoyed making these little things that do things, I guess.
Okay. Cool. Thank you.
Mm-hmm. Any other questions? Happy to answer off-topic ones too. I'm here.
That being said, I do have actually an on-topic question.
Okay.
In your presentation, you talked about the fact that you saw these vertical associations in the delay peaks in your data. But do you guys have any idea sort of what real aspect of the FPGA might correlate with that? So, or like
why they're
wires,
in vertical columns?
Yeah. Why is it? Why is there something that's a vertical relationship on the board that doesn't exist in the horizontal direction?
Yeah. So
vice versa.
That color plot didn't give the most accurate depiction of the board, but essentially, because there's a lot going on there. It's a very complex device, and it took all summer for us to understand it at the level that we could even do this rather simple thing. But essentially, you saw some gaps in that color map. Some of those gaps are just blocks specifically designed for routing. And we did notice that some of the faster labs were next to those routing blocks. So it might be how the manufacturing process works, that sort of the characteristics of those semiconductors are slightly different because of how they're placed. It's kind of hard to say. So the process node this was made on was TSMC's 28 nanometer lithography process. So TSMC makes almost all the computer chips in the world out in Taiwan because nobody else can seem to do it right, aka Intel. That's why AMD's been doing good lately. But I couldn't find a whole lot of details on their manufacturing process. I tried to dig around, but they're a bit tight-lipped about that being practical monopoly in it. But yeah, basically that would be my guess, is either it has to do with the routing or some process, node-specific process, like, well, basically how it was laid out with the lithography, that those semiconductors end up with slightly different properties.
Fascinating. Thank you.
Mm-hmm. Yep. Actually, an interesting thing about this board too is that it's not only an FPGA. They actually stuck a CPU on this thing too, and it can boot Linux. Which for those of you who, most of you probably have heard of Linux, but it's a free and open source operating system like you would have Mac OS or Windows. And it runs on rather low computational powered devices. So on this little board here, you can actually boot up a full Linux operating system next to the FPGA and have that interact with the FPGA, and the FPGA can do some specialized computations and communicate it with the operating system on there. And if this thing even has an Ethernet port, you can network it. But that's very hard to do.
I have a
Yeah.
question then. So should I buy an FPGA because I want to use Linux on it, or because I'm interested in configuring circuits?
Hi, Caitlin. Well, you should get an FPGA if you want to work with circuits. If you want to just run Linux, a Raspberry Pi is far cheaper.
Is it possible for the FPGA to, using that onboard CPU, self-modify? Could you have
Yes.
it? Could you have a program which essentially auto-optimizes a circuit or tries to auto-optimize a circuit?
Well, so there's actually a lot of optimization simulation software built in with the IDE that like comes with these boards. It's packaged with them. But so the CPU in that whole system can reprogram the FPGA on the fly, but it can't compile new designs on chip. It's a very computationally intensive process. I have an overclocked i7 desktop, and it takes like upwards of 7 minutes on some compiles. And Caitlin with her laptop, much longer. But
Back off.
but yeah, so, but the fact that it can reconfigure itself is very cool. That it can like reprogram itself to other things. And yeah, but you'd have to essentially get those designs either on there. The files that they program them with are called SOF files, some sort of just binary block that some controller on the FPGA understands. So you could stick a whole bunch of those files and load them in different ways. But as for dynamic, likely changing the circuit on the fly, that's not something I think this board is. I don't think it's capable of that.
Yeah, I don't mean to jump in, but I also think like Nathan's question has the other fun part when he asks about it, like optimizing the circuit, that when you write like your circuit, a lot of the times you just write like the kind of skeleton idea behind it, and a lot of the nitty gritty happens in like the compilation, and it's like really expensive. So I think that's something interesting too, that you're actually pretty far away from like the actual circuit.
Yeah.
And actually
Yeah.
that causes us tons of problems in this
It
project.
does.
Yeah, it's just like bad.
Well, you should just program it manually, Caitlin. So basically we program these boards in something called Verilog. It's a kind of like a programming language, but it's a hardware description language. So it looks like C and C++, but it's not like them. You essentially define logic to execute according to different signals. You can define and place modules almost as if they were functions. You can have for loops even for defining and like placing a whole bunch of logic. But we kind of programmatically lay it out. We don't have to touch any of the low-level logic circuits, but it is an optimizing compiler, which has the problems that an optimizing compiler does in that sometimes it thinks it's smarter than you, because it is, but it does things we don't want. Our ring oscillators, for example, look very much like redundant logic to it. And if we didn't put a little flag in the compiler telling it not to get rid of them, it would say, that's redundant, I'm getting rid of that. So if we don't tell it, it just completely removes our ring oscillators, because it's like, why the hell would anyone make something so stupid? It just goes around in a loop. It doesn't even do anything.
In a word, this is slow. I don't care if it's slow on purpose. It's slow.
Yeah, yeah. Mm-hmm.
Too smart for its own good.
Yeah.
Not context sensitive.
Mm-hmm. Well, at least we can tell it to ignore itself sometimes. Another little FPGA I have that's about the size of a thumb drive. Its compiler does not have such features that I can tell. So I try to make a ring oscillator on it, and it just optimized it away, and like, well, tough luck, buddy.
Is there any way to program them more granularly?
Yes. Yeah. Yeah. Don't want to think about that. It's
I see.
very
Is that
complicated.
Would that be like analogous to programming directly in assembly or something?
I'd say it's probably, for a complex design, it's harder than assembly. I've written some assembly.
Sense.
This would be harder than assembly. Yeah.
Yeah, and even to get like increase like a finer level of control, you have to do so much. Like there was a grad student in our group who had to read the source files for the compiler to like get what he wanted, which is just preposterous.
Mm-hmm. Yeah, that was Noello. Yeah, he was very helpful in teaching us how to navigate the software and make it do what we want it to do.
Yeah,
Because,
Noella was like FPGA god.
yeah, because this expects that you're going to try to make a computer with it, essentially, like some sort of like processor that operates only according to a clock. But we're doing things asynchronously. We're doing things outside of those clock cycles, and it's very much not designed for that. They tell you not to do that with it, and it does not like it.
Why don't they want you doing things out of clock?
Well, so that kind of comes to one of the issues I mentioned with the problems of the registers not latching and the crossing clock domains, is that you can get what are known as metastable states. So essentially, all computers that low levels a whole bunch of transistors that trigger at certain voltage levels. But if those voltage levels aren't timed right, you may try to trigger off on something as that voltage level is rising. And if, let's say, you're going to trigger at 1 volt, but it's at half a volt, does it trigger true or false? You don't know. It's a metastable state. So that's the main worry, is you have to be very careful when doing this because you can get a lot of unexpected behavior. And that's why it tries to control for that. And we have to tell it not to.
Interesting.
Yeah, and I feel like Liam, just because I really hate FPGAs, didn't really make this seem bad enough. Like, nothing is sequential. Everything is executed at once, which is why a lot of stuff is driven by the clock.
Oh, yeah, yeah. If you write lines of Verilog, they do not just, like, execute top-down how you would expect with a programming language. You have to just think in terms of digital logic. So. Yeah, but as for fast data processing, these things are pretty cool. You can program do so many different things. That Cornell class I talked about, they had, of course, the people who did the Mandelbrot fractal zoom hardware accelerated on there. So this little board, they programmed logic gates to do a Mandelbrot fractal zoom, which is pretty fascinating. Another group used it for high-speed on-the-fly adjustments to levitate a marble with an electromagnet. So they could very precisely read its height and then adjust the current going through their electromagnetic coil to like keep it hovering there, which you would not be able to do with a normal speed CPU. You just wouldn't be able to analyze it that fast with a general purpose processor.
So this is the sort of thing you'd use to conduct any sort of experiment which needs to do or conduct any sort of process which needs to do very rapid, highly specific response computations. Like I call to mind something that got published about 2 years ago about using sound waves to trap a lattice of beads in the air and make images that can be interacted with out of them, because you can trap the beads in.
Oh yeah, was that sort of I thought I remember a similar thing being done with lasers. And essentially they were moving these dust particles around to make images.
Yeah, it was very similar to that, but they did it with sound. So they they trapped it in the nodes of the pressure wave of the sound, and you need to rapidly respond to how the beads respond to that, because the idea was to do 3D holograms that you could touch, because you can touch the beads and move them, but yeah, and the system can react to that.
That sort of on-the-fly stuff is something you want to use FPGA for, because you have direct access to the logic, as opposed to on a CPU, for example, you're going through buses, you're going through PCIe lanes, and there's a lot of delay introduced there, as well as a lot less fine control. So on this, you could make something trigger in a matter of picoseconds. That's not going to happen with a CPU, even if it has a clock speed of like 5 gigahertz. Like, that's only getting you 500 picoseconds. Right? Or did I do math wrong? Yeah. Yeah, I've actually seen even some people use these to emulate old computer architectures. I think there's a whole community that uses this board in particular to do retro gaming. They've actually emulated old console CPUs as hardware. So they actually run significantly faster than the old consoles, don't have to deal with the problems of an emulator because it is the CPU architecture.
Does that count as a tool-assisted speedrun then?
Probably would, yeah. Yeah, considering you could probably push it to a couple hundred frames per second on these boards. And
I certainly think you have to define that as a different category.
yeah, but there's quite a hobbyist group for that.
No, I mean cultural preservation of the early days of, art medium, essentially. I just want to point it out there to anyone if you have a question but don't have a good microphone or are not in an area conducive to talking, feel free to throw it in the chat. I can read them out. I just realized I didn't say that, and I don't want anyone not to ask something because they don't feel like they can talk.
Mm-hmm. Mm-hmm. Yeah, and actually another application we're using these for in our lab is to make what we call a pulse picker. Basically, we have a very high-speed pulsed laser, but it's too fast for the detectors we want to use. The detectors have a certain dead time after they register an event before they can register another one. So we need to essentially slow that down. So I take an FPGA, I sync up its clock to the laser's pulse, and then I can have it send out a pulse every 10 laser pulses. And that will control something that essentially lets it through. It can be like 2 adjustable polarizers that let the light through and then don't otherwise. So that's something I'm actually setting up now. I'm going to be finally going back into the PRB actually to get that set up tomorrow.
Congratulations on being let into the forbidden domain.
Mm-hmm.
Well, if no one else has any questions, I'm not seeing anything in the chat, and no one else seems to be piping up through a voice. So if no one else has any questions, I see no reason why we can't break a little early. It's a weird time. No reason to do things on ceremony alone. So provided I don't get interrupted midway through this, which I foresee is an entire possibility. Thank you for speaking, Liam, despite how tired you are today. We really and the short notice, we really appreciate that. This is really cool work. I'm sorry it's run into so many annoying snags, but I have both hope and confidence that you'll find a way through it.
Yeah, I mean, we transitioned to this project because we can't do it from home.
Yes, Joey?
I was just clapping because...
Oh, clapping.
Yeah, just clapping.
I always interpret that as a waving hand.
No, clapping because good presentation, and I appreciated the Minecraft analogies.
Thanks. Yeah, I showed that to my research group in front of my professors.
That's brilliant. Oh, that's good.
I was like, I made this in Minecraft.
I think Minecraft is actually a really good way of demonstrating that in slow motion.
Yeah, it's a good way to put it out. The first thing I did when we said we're going to do ring oscillators, I looked up what they were and I built them in Minecraft, so I knew how they worked.
Someone has built a literal CPU, so I guess an FPGA in Minecraft, so you know it's possible.
Minecraft is an FPGA.
Nope, couldn't keep a straight face. But I suppose you're right. So yeah, thank you for presenting, Liam. It's been great to have you, and thanks everyone else for coming. I hope you have a good evening, and take care.
Hold on real quick, Nathan.
Yeah.
I'll plug again. I think I said this last week where, if you want to talk about your research and get practice for when you do it at APS or grad school, you should for sure email us because I think the world is your oyster on when you would want to speak. We would really appreciate anybody who wants to. if that's something that interests you, email one of us, and we can definitely fit you in. That's all I had. That's my spiel.
No, that's an excellent point. I think I mentioned last week that we were going to send an email announcement out about this. We're still going to send an email announcement out about it. I've been just a little swamped this past week and haven't been able to get that out. But yeah, thanks for bringing that up, Sam. And yeah.
Yeah, I'll see if Dr. Guthrie or Dr. Lafayette will be willing to give a talk, since we're pretty short on speakers this semester.
I wouldn't worry about it. We'll find a way through. It's a weird time.
Yeah.
But yeah, thanks again, everyone, for coming, and I hope you have a good evening.
Yep, thanks for coming.